Thank you. So I'd like to talk about the speed limit of two-qubit entangling gates, specifically on a superconducting qubit platform. We've heard from other speakers about two-qubit gates with some with couplers, and we're interested in this project on how fast can we make them. So this is a collaboration between Colorado School of Mines and NIST Boulder. So here we have a little cartoon about how the maximum rate at which you can do a state evolution between two energy eigenstates is fairly well established in the last 100 or so years. But only, again, between two energy eigenstates. It's an open question as to how fast you can move between two arbitrary density matrices. Between two arbitrary density matrices. So that's one focus of this project, sort of the theory side is how can we better quantify that and develop analytical expressions for the maximum rate at which we can perform that state evolution. The second main idea of this main focus of this project is connectivity, which is our theory collaborators have found that as you increase connectivity, you can actually make this rate faster. So here we have two quantum processors, one from IBM, which has a two-dimensional nearest neighbor connectivity, and one from the University of Maryland, which is an ion trap that has all-to-all connectivity. And as you increase this connectivity, we found that you can increase the entangling rate, and we're interested in sort of seeing how that happens. And just sort of another small cartoon of sort of why that happens. If you wanted to do a state transfer between a qubit over here and a qubit over here, the state sort of spreads out over all of the connected qubits, and it sort of performs a wave that moves down, and there's a constructive interference that occurs that helps boost the rate at which you can move the state from here to here faster than if it were just a single 1D chain. So here we go. So we heard, especially by the folks from IBM earlier, about tunable couplers and about the relative lengths of the two-qubit gates and the single qubit gates. And typically, if you can turn off your coupling between your qubits pretty reliably, then you can make that you can make your single qubit gates quite fast because you don't have to worry about that coupling causing sort of unintended consequences on the other qubit. Obviously, that's not necessarily a reality quite yet, but that's sort of a hope for many people who work with tunable couplers. So actually, before I move on to that, that's important. That's sort of the motivation behind this project, because it's then the two-qubit gates that are very long, and so we want to make them so those are going to be the bottleneck for any algorithm. And with a finite sort of coherence window, we're going to have to get increasing circuit depth, we want to make our gates as fast as possible. So we're sort of focusing on the bottlenecked gates. So again, this was just sort of another study by Murphy and collaborators, where if you have a spin chain, you want to move a state from one side to the other, and you have a sort of mediating magnetic field that creates that spin interaction. The wider you make that magnetic field, the faster you can transfer the spin from one side to the other. And that's it's sort of another motivation. We want to see if we can harness that for generating entangled states. So this is sort of where we get into the bulk of the theory behind this project, which is that while the analytical expression exists for going between two energy eigenstates, we've started to develop the analytical expressions for generating entangled states. And for some protocols, we can get an analytical expression. So here we have a speed up. So here we have a two-qubit fidelity curve where the x-axis is the gate duration, and this sort of defines your speed limit, that we get to a normalized gate time length of 1 at an infidelity of 0, which means we've hit our target state. But for 2 qubits, it gets to 1, and for 3 qubits, when you add this third blue helper qubit, you can get to 0.82, which is almost a 20% speed up, which is exciting. Again, this is only for some protocols, and it also assumes a free particle Hamiltonian of this form. Here we have just a little cartoon of all-to-all connectivity, and the exciting feature of this is that, and this may be more exciting for people who work in say neuromorphic quantum computing, where you really want lots of connectivity, also for some of the trapped ion people, but you can get a dramatic speed up of O of 1 over square root of n, where n is the number of qubits, compared to O of n for a single spin chain, or O of 1 for direct connection. So if we're talking about a quantum processor with 1 million qubits, and especially if it has a very high degree of connectivity, if we can develop protocols to leverage that connectivity to speed up all of our entangling gates so that we can fit more gates in our coherence window, that would be really exciting. So this fidelity curve is sort of what we set out to. I'm more on the experimental side, so what we set out to try and show and demonstrate. So the device on which we performed our initial measurements is a two capacitively coupled transmods, dispersively coupled to readout resonators in this hanger geometry, and it's got a sort of a standard Hamiltonian that we used for designing the circuit. And they have a static ZZ coupling of about 7 megahertz. It fluctuates a little bit, but as many others have talked about in this session, the ZZ coupling is due to interactions with non-computational basis states, the 0,2 and the 2,0, creating an asymmetry across these states. So we're dealing with a chip that has fixed coupling. A lot of really great work has been put into developing the system at NIST. And our T1 and T2 times are about 80 and 50 microseconds respectively. So which is plenty long enough for the experiments that we're performing here. So on the previous slide, we talked about this only working for certain protocols. The protocol in which we got that 20% speed up, unfortunately, requires very fast single qubit gates. So this is what we talked about before about, on many quantum processors, especially if you have a tunable coupler, which we don't have here, you can get extremely fast single qubit gates. Here we don't have a tunable coupler, so our single qubit gates, as I'll show on a subsequent slide, are quite long. But this protocol is a single qubit gate followed by a dark state evolution followed by another single qubit gate on both qubits. And because we can't really assume that those are instantaneous, we need to find another way for this particular experiment until we can get a new, more suitable chip. So this is the experiment. Because we don't have those very fast single qubit gates, we're actually working with a numerically determined speed limit as opposed to an analytically determined one. And we're using grape optimization, an optimal control protocol, to determine that based on our Hamiltonian, including the drive, but also based on the maximum drive strength that we have available, which is not infinite due to power broadening issues. So here we have two graphs. So if we look at the blue curve here, this is the predicted infidelity curve for our 2-qubit system. And as you can see, it doesn't quite asymptote to this nice value of 1, which is what we were hoping for. Because we give it artificial constraints for the drive strength, it can't quite get to that 1. However, we've run simulations on what an improved chip, which is still a very practical and realizable chip, and that one could get very close to this speed limit of 1. So that's sort of in the future work category. So this is what we'd like to demonstrate using this optimal control pulse protocol, which is here. We have our optimized pulses in red, and you can see here in these two are our tomographic post rotations, and this is called the 2-axis gate. We'll have a paper coming out shortly about it. This is what we use to compensate for the always on coupling so that we can do single qubit rotations, because just a straight Rabi drive doesn't work due to the nature of the coupling. But you can see they're quite long. They're almost 200 microseconds or so. They're 200 nanoseconds. So they're quite long compared to our drive.
Okay, so about a minute warning.
Okay, thanks. I'm almost done. So this is the data that we got. It tracks pretty nicely. There are a couple features that we're interested in understanding more about, but we got a fidelity of 97.3%, which we were pretty excited about for a first pass. Future work, we want to get even closer to that 1.0, that unity speed limit for 2 qubits. And then obviously, the main feature of this is we want to demonstrate a speed up. So we've already developed and fabricated a 3-qubit chip that has weaker couplings. And the plan is to remove one of the junctions to compare it to the 2-qubit case, which actually doesn't affect the coupling between the 2 qubits of interest that we're trying to entangle. We want to, in the far future, develop or explore even higher degrees of connectivity with a flip chip design, where you get an all-to-all connectivity, and hopefully at some point demonstrate that O of 1 over square root of n speed up. We want to, on sort of current devices, see if we can develop these protocols that leverage existing coupling. So, we're not sure if you would want to be adding qubits just for this whole purpose of speeding up these gates, but if you can leverage existing coupling, that would be sort of a nice little boost. And obviously, we want to be realistic about qubit crosstalk. sort of related to that last point of with these noisy devices, to what degree is adding additional coupling to speed up the gate not going to completely deteriorate the performance of your device? And does this kind of scheme actually make sense? With that, I'd like to acknowledge the NIST, Boulder, and Minds groups, as well as NSF and the University of Chicago QuaisNet program for all their support. Thanks.